Relativity is a simple concept. It asserts that the fundamental laws of physics are the same whatever your state of motion. For the special case of observers moving at constant velocity, it is fairly intuitive. Imagine Niall in his chair at home and me in an airplane. We both can pour a cup of coffee, play ball, shine a flashlight, and have the same laws of physics apply. In fact, there is no way to determine which of us is in motion and which is at rest. Therefore, Niall could perceive himself at rest and the plane in motion, and I could perceive myself at rest and the earth gliding past me. There is no absolute right. All that can be said is that each of us is moving relative to each other. Me and Niall could also work with relative to planets, stars, and galaxies. The special theory of relativity that Einstein developed in 1905 applies to this special case, hence the name, a situation in which the observers are moving at a constant velocity relative to one another. This is referred to as inertial reference system. The concept of relativity began in 1632 when Galileo proposed that the laws of motion in mechanics were the same in all constant velocity reference frames. Imagine that sound waves are coming at you from a distant boat horn, rippling through the still air at 343 meters per second towards the shore. If you jump on your jet ski and head towards the horn at 40 meters per second, the sound waves will be moving towards you and zipping past you at a speed relative to you of 483.2 meters per second. Since the sound waves travel at 343 meters per second, you add the speed of the ski boat, which is 40 meters per second, therefore giving us the speed of 383 meters per second. What we are going to do is put an aerial on top of the S frame and a dangling wire under the S prime frame, such that as S prime passes S, the dangling wire touches the aerial. And two clocks on both frames are synchronized and both start in t equals 0. We might imagine that they will be synchronized, but soon we will discover it is not true. After a short period of time, there is a light flash some distance away. People on both frames of reference can use their frames of reference to get the distance that the light is far away from them. S would say that the light flashed when it was x away and the time was measured t. We will say that the S prime moves to the right when the flash occurs relative. S prime would say that the light flashed x prime away and the time measured was t prime. You can see that the x equals x prime plus the distance of the separation between s and s prime. Since the relative velocity is v and the time that has passed is t prime, the d equals velocity times t prime. So now we could say x equals x prime plus vt prime, and also say x prime equals x minus vt. Now as previously, we learned about relativity. But what happens with light? Is it relative or not? Einstein asked. The Michelson-Morley experiment in 1887 explained something peculiar. Let us see what happens. We discovered that light is not relative. Both reference frames discovered that the speed of light is exactly c. So if I move 30 meters per second with the light, an observer will measure the speed of light to be c, not 30 plus c. One of the things you can say is that the person measuring the speed measured incorrectly. Since velocity equals distance over time, the people measuring the speed are either using an incorrect ruler to measure distance or an incorrect watch to measure time. So now let's go to our two frames. Now when S prime passes S, not only will it cause the time to synchronize, it will cause the signal to the far distant light to switch it on. Of course, when the light actually appears, S and S prime will be in this position. They are both entitled to say that they are stationary. S can say x traveled in t, therefore c equals x over t. S prime can say x prime traveled in t prime, therefore c equals x prime over t prime. But we know from Michelson and Morley, speed of light is constant. Since x and x prime are different, it shows that t and t prime are not the same. So, each of them alleges that both of them made some kind of errors in distance or time or both. We assign this error called gamma. S prime says x equals gamma times x prime plus u t prime, while S says x prime equals gamma times x minus u t. They both use gamma because each of them are assuming one of them are wrong. We can find the gamma by taking the two equations and multiply them on the left and right side, which now gives us x prime equals gamma squared times x prime plus ut prime times x minus ut. And now simplifying it gives us x prime equals gamma squared times x prime x plus ut prime x minus x squared ut minus u squared t prime t. Now we can substitute t equals xc and t prime equals x prime over c, therefore giving us x prime equals gamma squared times x prime plus ux prime over c x minus x squared ux over c minus u squared x over c prime. Now we divide by x prime. That gives us 1 equals gamma squared times 1 plus v over c minus v over c minus v squared over c squared. And now we isolate gamma, which equals 1 over square root of 1 minus v squared over c squared. This is what we call the Lorentz transform. Now, if we apply this transform, we get x equals x prime plus u t prime over square root of 1 minus v squared over c squared. And we also get x prime equals x minus ut over square root of 1 minus v squared over c squared. So what happens when v becomes very small? Then the term in the roots will reduce to 1 and you get the normal Newtonian mechanics. Basically saying gamma is not relevant because the error is now very unobservable. But when u approaches c, gamma is now relevant. This is known as becoming relativistic because gamma, or the error, is now becoming observable. If distance is applicable, then time must be also applicable. X prime equals x minus u t times gamma, and t is changed to x over c, which gives us x prime equals x minus ux over c times gamma. Now if we divide the equation by c, we get x prime over c equals x over c minus ux over c squared times gamma, which gives us t prime equals t minus ux over c squared times gamma. And now for the x's point of view, x equals x prime plus ut prime times gamma, which gives us x equals x prime plus ux prime over c times gamma. And now divided by c gives us x over c equals t prime plus ux prime over c squared times gamma. And now t equals t prime plus ux prime over c squared times gamma. So what is this telling us? It is telling us that when speed is relativistic, in other words, getting to the point where gamma ceases to become 1, that the distance in time measured by an observer will depend on the speed of the distance between s and s prime. Since this is a little counterintuitive, let's observe this more. Let us imagine that we create a very simple clock. The clock is consisted of two mirrors 1 meter apart. A light pulse travels between the mirrors and is reflected back and forth. Every time it hits the lower mirror, it hits a counter, which clicks by 1 count. We know the speed of light is 3 times 10 to the power of 8 meters per second. And we know the journey from top to the bottom mirror is 2 meters. So if the light pulse completes 1.5 times 10 to the power of 8 cycles, 1 second has gone by. But now let's imagine the mirrors on the spacecraft S, and we have somebody else observing it, and he is looking at the clock relative to the observer. The spacecraft is moving at velocity v. When the light pulse leaves the bottom mirror, the spacecraft will be here, but when the light arrives at the top mirror, the spacecraft would have moved, and therefore the mirror too. So the light pulse would have gone in an angle. Similarly, when the light pulse comes back down again, the time it takes from getting the top mirror to the bottom mirror will mean it moved slightly again. Therefore, the light would have moved in an angle again. The observer says the distance that the light pulse has traveled is further than 1 meter because it is in an angle. And since light is invariant, it must have taken longer to get to the mirror than to the person inboard thinks. This concludes that if you observe a moving clock, it would say that the clock is running slower. Every observer observing a moving clock will see that the moving clock is moving at a slower rate. Now let's look at what happens if S and S' are observing a particle moving at a certain velocity. Let's suppose the particle is moving on the S's frame of reference, and let's suppose it is traveling at a velocity v. S', however, observing from his spaceship, which is traveling at speed v relative to S, will measure the velocity of the particle w. V will equal x over t, and w equals to x prime over t prime. And now we are going to expand this equation, which gives us x minus ut over t minus u over c squared x. The gammas had actually cancelled out, and now we divide the terms by t, which gives us x over t minus u over 1 minus v over c squared x over t. Then this gives v minus u over 1 minus u v c squared. And similarly, it works both ways. V equals w plus u over 1 plus u w over c squared. If w equals c, the answer is also c. This is what Michelson and Morley predicted. Here, we see that Michelson and Morley was correct. It doesn't matter what the relative speed is between S and S'. If a particle is traveling at the speed of light on S, it will also be measured as traveling at the speed of light by S', irrespective to what the relative speed is between them. Let's take the event on S's frame of reference, and let's suppose the duration is t seconds. S is entitled to say he is stationary, and therefore x is 0. S' says that t' equals capital T minus u over c squared times x divided by square root of 1 minus u squared over c squared. Since x is 0, t' is now equal to t divided by square root of 1 minus u squared over c squared. Let us suppose that S' has a rod length of L'. S traveling at the relative speed of u measures that rod, and says that as length of L. Both are measuring the length at time of 0. The two ends of the rod are measured simultaneously, that way you can get a correct answer. S' says L' equals L minus 0 because of no time difference, divided by square root of 1 minus v squared over c squared. In other words, L equals L' times square root of 1 minus v squared over c squared. This means that a moving rod appears to be shorter,